Okay, so let's go in and look at what our, before we look at .cfg files, let's create the mesh. So we are now in Qubit. I have set my directory to examples 2D greens functions reverse. So let's open up our journal file. So mesh try3.jou. So the first thing in our journal file is we're going to play back the geometry. So let's open up our geometry. Using apropos to set the units, we reset, we turn off undo. So not much see there. Now we're going to create our block. So we're going to go with a block that's 150 kilometers by 80 kilometers. And we're using apropos to set the block width, length. And in this case, with this 2D example, what we're going to do is we're going to create a block, and then we're going to extract just the cross section. So here we've created the block. And so I can show you this, that we have a block with sort of a thin out-of-plane dimension. And then we're going to extract a mid-surface between surfaces 1 and 2. So we've created our cross-section by using the mid-surface command, and then we're going to delete the volume. And this provides just a simpler way to create, rather than having to create sort of vertices and then curves and create a surface, I just created a block and then took the mid-surface. So it's essentially a shortcut to creating the surface rather than building it up from vertices. So now with our surface, we're going to split. So I've split my surface, and now we're going to extract just the coseismic portion. So we have to first split our entire surface, and then we're going to split that curve further for just the portion where we want the faults, and we're going to name that curve fault surface. And so if I look at, I've split my curve here, and so this is going to be the fault where we'll compute the greens functions, and then this is sort of the extension of that fault. And it looks like we have a question here. So this is asking about generating greens functions in the case of a dynamic simulation. Currently, our greens functions are limited to just static seismic sources, and that's due to the fact that we have not yet extended our output to handle impulses as well as time steps. So in our output for the static greens functions, the first dimension is the impulse number, which in our dynamic simulations is the time step. So essentially, we're using the same schematic or layout of our output in greens functions, but replacing time with the impulse number. To do dynamic simulations, we'd have to further extend that out to a 4D output. And so that's something that we'll be working on in the future. Good question. So here's our geometry, and then we do an imprint all, merge all, just to make sure everything's cleaned up. So nothing was needed to be merged. So that's creating the geometry. In this case, it's pretty simple, just a dipping fault. So let's go back to our mesh file. And so the next thing we're going to do is we're going to set our nominal discretization size to 1 kilometer, and we're going to use triangle elements. So we set the scheme here to trimesh. Now all of our discretization size information is in this file called gradient. So let's open up that journal file. And what this is going to do is we want to grade the mesh away from the fault. And so in Green's functions, we're specifying a unit impulse right at the fault. So we need relatively high resolution to resolve that unit impulse right around the fault. And our mesh resolution will actually dictate the resolution of our impulses. So we'll have a 1 kilometer length scale for our impulses on the fault. And then in our solution, because we have isolated slip, we're going to have the deformation will get smoother and smoother as we go away from the fault and where that impulse is applied. So that means that we can use a much coarser resolution as we go away, as we increase the distance from the fault. And so we're going to set a bias factor of 5%, so a bias factor of 1.05. That means that as each cell, as we go away from the fault, will be 5% larger. And so that is a geometric progression. And so we'll have relatively coarse cells away from the fault where this solution is very smooth, so we're not decreasing our accuracy, and then fine cells near the fault. And this is an apropos function, which tells us our discretization size based on the length of the curve, our bias factor, and where we started. And so this we use this function so that when we're doing biases, we can quickly compute what the discretization size is as we go away from the fault. So here we're computing what our discretization size is at various vertices. So the first, this is our, size at vertex 11. So let's ask Qubit to locate vertex 11. So vertex 11 is over there in the corner. And so we're going to say what our dx start is the discretization size dx. So we're going to start at 1 kilometer. Our curve, we're using curve 19. So let's locate curve 19. So we're going to we want to compute the discretization size at vertex 11 for our current bias based on the bias on curve 19. And so this function is basically, we give it the ID of the curve, we give it our discretization size where we're starting in that curve, and tell it to compute, call this function, and we're going to assign that discretization size to dxa. And so we're going to do that for a number of curves. And so you'll notice that we'll use curve 20 and vertex 12, curve 22, and 13 and 10. So let's locate, curve 20. So there's curve 20, that's in the opposite direction. And also curve 22, locate curve 22. So down here at the bottom is curve 22, so we're going to do a bias on all of those curves. And then now we're going to set this curve, on all of those curves, we're going to set the scheme to default sizing function none to reset everything. And now we're going to specify our discretization size. So let's review. So right now, that's what our discretization size looks like. Here's our fine discretization. We've ended up on sizing scheme none didn't seem to take effect. But now we're going to specify on those biases on our curves. So 19, 20, and 22, that's where we set our discretization size dxa, dxb, dxc. And so these are our first curves there. Go away from the fault. So our fine size is dx because we're starting at the fault. Our bias factor is our coming from our bias factor that we set, 1.05. Then we're going to start at vertex 14 and 15. Yeah, it looks like we have an error. So I think we need to go back and let's make sure that we've got everything set up properly. So let's regenerate our geometry and let's start at the top of our gradient again and go back all the way. Let's see where we are. Preview surface. Oh. And it's still a little perplexed. That looks like that came better. There we go. Now you can see we specified a bias along our curve away from the fault on the ground surface to the left, to the right, and to the bottom. And now we want to specify our discretization sizes around those other curves. In that case, we're going to use, see now we're making use of assigning the discretization size DXC. So curve 21 will have a uniform discretization size DXC. And other curves. So here, let's look at curve 18. So rotate size at one end to a discretization size at the other end. It looks like I'm having an issue of my vertices. So start vertex 11. So where is vertex 11? So it looks like my curves are being numbered differently. So this could be an issue of we've switched from qubit 13 to qubit 14 because this worked fine for Charles yesterday. So this curve over here is curve 14. So let's switch that to curve 14 and see if this is, and so locate vertex 12. And vertex 12, then I'm going to do curve 16. So that's correct. D to C curve 18. So that looks correct. So it looks like we had a typo here on .cfg file. So let's redo all of these and see what we get. So let's see. It looks, if we look over here on our left side, we're getting on the ground surface we have a nice bias. We have a bias. You can see our discretization size increasing as we go down with depth. As we come down below the extension of the fault, we have a nice bias. We have a bias here along curve 18, and then also along here on the right side. So looks like we had a typo in our journal file about which curve we were using, so we needed this curve 14 here. So this line here, A to D, that should have been curve 14, and I believe we had curve 18. So we'll make sure to update that in our code repository. So this is that was our discretization size. So we have a nice smooth variation discretization size away from the fault, thanks to our bias function. And so now we're going to specify for the whole surface, we're going to use this sizing function bias starting on the curve's fault surface with a factor of bias. And so that by doing the surface, what that does is it gives a hint to the surface that when it's doing the meshing, don't just look at the discretization size on the curves, but also look at the discretization size within the domain and take the bias into account. Sometimes I use the sizing function bias on the surface. Sometimes if I have a small enough volume, we still get a pretty good smooth mesh just relying on the discretization size from the curves. So we've done our gradient. Now let's mesh the surface. So let's zoom in here. If I click on it, there you can see the mesh. So we have a nicely graded mesh away from the fault, and nice, relatively coarse away where we expect a very smooth solution. So we'll run smoothing on this to try and get the absolute best mesh possible. Generally, mesh generation is extremely high quality in 2D without any smoothing, but we have our mesh quality. We were aiming for condition number 1.3, which is very, very good. Now we'll do the boundary conditions. These boundary conditions are set up in the same way that we've done for our other cases. So let's just very quickly look through our boundary conditions. So that was in the create BC journal file. So again, we create our block. We're just using a single material, so both surfaces 8 and 9. Create for our node sets, we do a group, and then we create a node set from that group. So let's look and see what we ended up with. I'm going to turn off the mesh to make it easier to see our groups. Look at our boundary conditions. Oh, sorry, there's our blocks. So there's our elastic block. And for our node sets, there's our faults. There's our X positive, X negative, Y positive, and Y negative. So pretty straightforward, just our boundaries, and we use the curves on the boundaries to identify the nodes on the boundaries. So final step is to export the mesh. So we've exported the mesh. We have additional questions here. It looks like we're getting at least one question. So how do we decide on the value for the bias factor? And so it is somewhat intuitive in terms of, it's something that's definitely worth experimenting with. If you use a bias factor of like 1.1, you'll see that the mesh coarsens extremely quickly. And you can just you'll end up starting, your element quality will start to deteriorate at that point because it's coarsening so quickly. If you use a very small bias factor of, say, like 1.001, you'll see that it is a very, very gradual increase in the discretization size. So for dynamic problems, I've played around with what that bias factor is. For dynamic problems, I usually don't go above 1.02, and that's when I'm doing a spontaneous rupture simulation along the fault. In these quasi-static problems, and static problems, it really depends on what you're imposing on the fault, and sort of also your spatial variation in things like material properties. And so in our for example, our subduction case that we did in our 2D meshing example in session 2, Charles looked at the quality factor, the condition number, you could see that the condition number, especially in the crust, was starting to get large right near the boundary. And that's because we had a geometric constraint in terms of we had this layer that we were meshing separately, and our discretization size was starting to get larger than the thickness of that layer. And so in that case, we were starting to get distorted cells because we were coarsening and trying to impose a discretization size bigger than the size of our geometric feature. And so, in this particular example, we don't where we have the fault intersecting the edge. Everything else is essentially we don't have much of a spatial dimension, and so in this case, if I was trying to resolve something like that size, I wouldn't let my bias factor be so large that that my discretization size was getting bigger than my geometric features. The best way to really evaluate and test whether your bias factor is too big or not is to run, say, a couple bias factors right around the value that you think you need and look for convergence of your solution. If your solution has converged to a value as you decrease the discretization size, then you've gotten to the point where your solution is not sensitive to the bias factor, and you can be confident that you have resolved the solution appropriately. And that's really the case for sort of all of these problems. You want to generally, as we've recommended, you start with a coarse size, and then you refine it, and then you look at convergence to see that have you resolved the quantities of interest. Any other questions on the meshing in this case? Okay, well, I think we need to move along. So we've done the meshing, so let's exit out a qubit here. Let's look at our .cfg file. We'll load up text editor here. So we are now in 2D Green's functions reverse. This is our pilot app file. So this is going to be our basic parameters for this problem, whether we're doing our fake data or doing our Green's functions. So in this case, we turn on both a time-dependent problem as well as a Green's function problem type journal files. In all cases, we're using implicit time stepping. We're using a linear solver. We're importing the mesh from qubits, so we want information about that. We're going to turn on output from both kinematic faults as well as impulse faults, as well as our elasticity implicit. So that's all the information that will be sent to standard out. Our mesh generator here, we're using qubit, and our file name is meshtry3.exo for our Exodus file. We're going to reorder the mesh to try and optimize the runtime. We have to tell it the default is 3-dimension for the mesh generation for a 3D mesh, and so we need to tell it that we're doing just 2D for both the coordinate system as well as the problem. We're going to change the normal non-dimensional length scale to be 1 kilometer. And we're going to use our non-dimensional length scale of 1 second. That's going to be our default in this case for our well, I think we're doing a static simulation for an earthquake, so we'll look into that. Total time, 0 seconds. So in general, we're going to say we're doing static simulations with a time step of 1 year. So our relaxation time right here is sort of quite different than our time step, and we'll see how that plays out. On elastic material, so here we're going our problem, materials elastic. We're going to use elastic plane strain. We're in a 2D problem. the default is 3D elastic isotropic. So we need to change that from the default. And so our material properties, we have just one material. The nodes or block ID from Qbot is 1. Spatial database mat elastic. And our integration scheme, we're using triangles, so that's in the fiat simplex family. And since we're using 2D mesh, so our cell dimension is 2. For boundary conditions, very simple default boundary conditions. We're going to use the zero displacement database to specify zero displacement on the boundaries. So we constrain the displacement degree of freedom perpendicular to the boundary. So on the x positive face, for x positive displacement boundary, we use the node set face x pos. Boundary degree, the degree of freedom we're going to constrain is the x degree of freedom. Same thing on the negative side, corresponding node set, x degree of freedom being constrained. On the bottom boundary, y negative is the name that we gave it in our array up above. Node set is face y negative. We're going to constrain the y degree of freedom, which has the number 1. Our fault, just one fault. So interfaces is this array with just a single fault. Our material ID for the fault is 100. That's for our cohesive cells. And node set from qubit is false. And again, we have fiat simplex cells. We're now one dimension lower than our domain. So instead of a cell dimension 2 that we had for our domain, for our fault, we have a cell dimension of 1. And our output, we're going to output. Now we're going to have a little more complex output. We're going to do the domain, the ground surface, as well as points. And so for the points, we use the output solution points component. And for the ground surface, output solution subset corresponding to a surface on the boundary. We're going to use the Hdf5 output. So for the domain, that's data writer Hdf5 mesh. For the ground surface, we're going to write out the displacement field over a submesh. So it's called Hdf5 submesh. Now here we're going to look at our output points. For output points, there's 2 pieces that are particularly important that are new. So there's the coordinate system of how we're specifying the points, as well as a file with the information about the coordinates of those points. So this, I should really move this up there. So these 3 lines say, get your coordinates of the points from the file output points.txt. Those coordinates are written in a coordinate system with a space dimension of 2 and a units of kilometers, just to make it easier. And we've set this up such that, in many cases, you're going to be getting your coordinates of points. You're going to want to just simply convert them from, say, latitude, longitude. And so instead of putting in a header that has all the coordinates information, we put that within the pilot configuration and parameter settings so that you can reuse your coordinate file, whether using GMT or some other software. So we didn't want to have a separate file format. So we just have basically XY points within the output points file. Then our writer is Hdf5 mesh. Again, we're doing just a very simple output of mesh points. Our fault output, that's it's a submesh because it's at a lower dimension, and then the field is defined over that lower dimension, so that's why we have sub-submesh. If this is confusing, we suggest looking at the pilot manual, and fortunately in version 2 that'll be coming out shortly, we've been able to simplify this, and we've gotten rid of this distinction between meshes, submeshes, and sub-submeshes. So something to look forward to. We're going to, in this case, not write any information about over the state variables or materials. So we've turned off outputting U, lambda, And the density, we've also turned out writing out stress and strain. And our solver parameters, using a linear solver exclusively, additive Schwartz preconditioning, our tolerance, relative tolerance of 10 to the minus 8, absolute tolerance of 10 to the minus 10, give it a sort of a large number of maximum iterations. We shouldn't need that many iterations. We'll monitor the solution, and please tell us why the solution converged or did not converge. So that's the pilot app file. Now let's look at our fake data. So this is going to be the simulation for generating our fake forward simulation, fake observations. So this is limited essentially to just the fault in the output. So we're going to use a kinematic fault for prescribed slip. Then our slip distribution is in the file eqslip.spatialdb. It has a linear variation. And our slip time, we're going to use a uniform database. We're going to use static observations. So we say that tell the slip time to start at 0 years. And the default slip time function is a step function, so we don't have to change that. And here for output, all we're doing is setting the file names for output. So domain will be eqsim.h5, ground surface. We append the dash ground surface. For the points, we do dash points. For the fault, dash faults. And our state variables, which we don't expect to show up in output, dash state bars. Any questions on generating our fake forward data? Okay, well, let's run this. So here we are in our reverse directory. So to run the forward simulation, I just type pilot eqsim.cfg. And so it ran. Here's all the log information from PETSI. So did our solution converge? So it did take 98 iterations. That's additive Schwartz. Matt will talk about in the next session being able to improve that quite a bit using alternative preconditioners, converge due to the relative tolerance. And so pretty straightforward in terms of just computing a single static simulation. So that is pretty straightforward. Now let's look at the output. So switching to peer review. Let's get to the right directory. Examples, 2D, Greens functions, reverse output. So let's look at the ground surface. And let's not look at the fault. Let's keep blind about what the fault slip actually was. So let's just do eqsim, do the whole domain here. Hit apply. So here's what my deformation looks like. Looks like we have a reverse slipping fault. And I'm in 2D with Hdf5 output, so you'll notice that I can't immediately warp my solution, and so I have to actually create. And you'll notice that here I have displacement X and displacement Y. So my displacement field has been broken up into just the two components. And this is due to the fact that in our Hdf5 output file, we wrote two components of displacement. And so we can't tell ParaView. ParaView is expecting for a vector displacement, for a vector field, it expects three components. And so in order to create three components for a vector field, we use our little calculator up here, and we tell it, take displacement X times I hat plus displacement Y times J hat. And so we could also add in, and effectively we have implicitly plus 0 times K hat. And so this is forming our displacement vector. So in our resulting array name, we're going to, let's call it displacement vec. And so now up here, I can select my displacement vec. So here's the magnitude of that vector. And you can see now I can warp things. So let's warp by a factor of, I think, 1,000. And so there's our reverse fault. Notice our slip. So we've created a reverse fault earthquake. We have observations along the ground surface. So let's switch to our wireframe here. And then we'll bring in our observations. So that was at EQSIM points. So our points aren't very visible, so let's change their size. Try color. And change points. And there's point size, so let's make them point size 8. So there you can see the points where we have our observations, colored by X displacement, or if we color them by Y displacement. And there's my color bar. So my color bar is not centered about 0, so that's why the left-hand side is not all red. So what we're going to do is we're going to compute Green's functions at each of these points for impulses along the fault. So let's go ahead and do that. So we'll keep this. We'll delete where we are in pair view here. And go back to window here, text editor, EDX. So we're now going to look at the Green's function problem. So the first thing you notice is that instead of pilot app, this is specific to a Green's function problem. And so we, by naming a problem Green's functions and using a Green's function.cfg file, these settings or parameters will be, the Green's function.cfg file will be automatically read by Pilot when we tell it we have a Green's function problem. And so instead of prefacing everything with Pilot app, but we can just simply use Green's functions because that's the name of our component. So in previous cases, we could have created a time-dependent.cfg file, and whenever we ran a time-dependent problem, that file would also be read in. This is generally only really handy when you have sort of a fundamental problem type and parameters that are independent of anything else for that problem type. And so in our Green's function, we may have multiple faults, and so we have to tell Pilot that when you're computing Green's functions, compute the Green's functions for a specific fault. We can have other faults, and we could be computing the Green's functions for, say, stress changes on the other faults resulting from impulses on one particular fault. So we tell it that the fault ID or the material ID for the fault that we want impulses applied to is 100. And we're going to change the type of fault. And so instead of a kinematic or dynamic fault, we're using a impulses fault type. So that's fault cohesion and impulses is the name of the component. We tell it on which slip degrees of freedom we want the impulses applied. So we're going to apply them only to the left lateral slip, and rather than both lateral and fault openings. So that's left lateral is the initial or first component, so that's component 0. And we use this nomenclature left lateral because that is unambiguous in 2D. So even though in this case we have a reverse fault, our slip, sensitive slip in terms of how it's defined within Pilot is using left lateral and fault opening because they are unambiguous. And so then to define where the slip amplitude should be applied to the fault, we don't have to compute Green's functions for every single vertex on the fault. We can just limit it to certain patches, and so that's what this spatial database is doing. And we'll look at impulse amplitude. So wherever this impulse amplitude is non-zero, that's where the impulses will be applied. We're going to use nearest interpolation. And then our output files, we're going to preface everything with Green's functions. For our ground surface, we do -Green's function, points-points, fault-faults, and state vars-state vars. So let's look at what this impulse amplitude spatial DB file looks like. And essentially what it says is if you have, it gives just 2 points. So that's why we're using nearest interpolation. So anything that's closer to -18.0, use an amplitude of -1. If you're closer to -18.1, use an amplitude of 0. So what this is going to do is that every point below that's 18.1 kilometers or deeper will have an amplitude of 0. Anything shallower than 18 will have an amplitude of -1. And I believe I have locally modified this from what you will have. I believe there was a typo that we had +18 and +18.1. So with +18 and +18.1, everything was getting, those points are above the domain, so the closest point to the domain was this first line, so everything in an amplitude of -1. And this amplitude of -1, remember our center slip is specified in terms of left lateral. And so by using the amplitude of -1, we're going to impose impulses in the right lateral direction, which will give us our reverse slip in this case. Remember our fault was dipping down to the left, and so right lateral, when we look at it, will give us a reverse motion. If we were doing left lateral, it would end up being a normal fault. So that's what our how we specify and set up our Green's function computation. Any questions on our .cfg files for Green's functions? Okay, pretty straightforward. Let's go and run this. So here's a little bit of a departure from what we've done in the past. So we want to change the problem type and have it read in the Green's function. So what we do is we're going to, on the command line, we're going to set what the problem type is. So we say --problem equals pilot.problems.Greens function. And so this is telling Pilot, change the problem type to Green's functions. And by using a Green's functions problem type, it'll look for any Green's functions.cfg file. That's where all our parameters are, so we don't have to actually tell it to read in the Pilot app and Green's function.cfg files. Both of them will be read in automatically. So here it's running. You can see it's doing a bunch of linear solves. Look really quickly. You'll see that instead of saying advancing from time step to time step, it says I'm computing response to impulse 26 of 26. So it's going to tell you how many impulses it's going to compute, so that way you have an idea of how soon it'll going to finish. And then when it does each impulse, it'll say I'm doing impulse 1 of 26, 2 of 26, and so forth. Each one of those impulses has its own linear solve. Notice that it's not saying any, it's basically in preparing to run impulse, it's not recomputing our stiffness matrix, it's just setting the constraints, so it's just setting where that impulse is being applied to which vertex. Then it's integrating the residual and then solving an equation. So this, in addition to sort of having a user-friendly interface, we've also tried to optimize the computation in terms of we don't reset up our stiffness matrix. That doesn't change from impulse to impulse. All we do is recompute the right-hand side of our equation and then do the linear solve. So pretty easy to set up and run the greens functions. So now let's look at the output from computing the greens functions. So back to pair view. Open up our greens functions fault as well as our ground surface and our points. So our points we better display as points. So point size, I like that point size of 8. Seemed to work well. We'll display the Y displacement. On our faults, we can change on a line width. I don't see any color. Let's give me a different box. This is a newer version of pair view than what we tended to be using. I don't see line width here, so we'll just keep it at that line width. It's a little more difficult to see. And as we step through, so we have, as we go through in time, you can just make out that our impulse there is moving. And so as we advance in time, we'll see the impulse moving down the fault. And by using the reverse Cuthell-McKee, they tend to be moving in one direction, but occasionally they'll jump around. So there we jump forward, then we're going to end up going back. And so we had 26 impulses starting at 0. And if I go, let's see, here in the points, displacement Y, and if now I go back, you can see how the displacements on the ground surface are changing as in response to where I put my impulse. There, now there's my color bar. So then move forward, the displacement is changing. So there's all my impulse responses. Now we're set up to do an inversion. So we're going to go back and open up our text editor. So we can there we go. So if I go up one directory, there is a Python script called invertslip.py. And I need to increase our font size here. So this script, when we run it, will invert the fault slip. So it's going to read in our observations, it's going to read in our impulses, and it'll formulate the inversion problem. And so we're going to make use of NumPy as well as H5Py. H5Py is how we're going to read in all our output files. Here's these 3 lines right here are grabbing our information about the impulse responses. So to open up our Hdf5 file, it's just a simple one line. We tell it the name of the file. This is going to come from the command line. We're going to open it in read mode, and sort of on a Unix system to get the best performance, we're going to use the SEC2 driver. You don't have to provide the driver information. I believe the default is SEC2. Sometimes we're reading in really big files, and so we really do want to make sure that we're using the best driver. You can find information about the different drivers in the H5Pi documentation. So just do a Google search for H5Pi. Then to grab all the coordinates of the vertices is just one line. This is a Python notation to grab the data set geometry / vertices. To grab the slip, it's in vertex field / slip. And we're going to grab, there's 3 dimensions, and we're going to grab just the first component of the slip. And so before I go any further, let's go back and let's actually look in a little more detail at what an Hdf5 file looks like. So bundled with Hdf5 are some utilities. So if you just do an H5 and hit tab, and you'll see that there's things like a number of H5 commands. So there's things like H5ls. So if we run that on one of our output greensfunctions-fault H5, it essentially tells you what's in. It's like running the ls command on a Unix system on the H5 file. So it tells you what's in there. In this case, it says I have a geometry group, I have a time data set, a topology group, and vertex fields. That's not particularly helpful because it doesn't say what's in those groups. So I like the H5 dump-n command, and it's going to tell me everything that's in all the different groups and data sets within the Hdf5 file. And so it lists it as it is, like looking like a directory. So I have a group / geometry. Within that group, I have a data set. This is, you'll notice how is the same syntax that I used in the Python file, and it's also the same how you would use it in a MATLAB file to specify that I want the coordinates of the vertices. So I just say, give me /geometry / vertices, and it's going to go in, get the data set. I don't have to tell it, skip so many bytes to get to the vertices information. I can just tell it and extract just the components of the Hdf5 file that I want. And so to really get the slip data set, or field /slip. I want to see the whole data file. I can just do H5 dump -n. If I want to do just the header information, I can do -H. This gives me not just the hierarchy, but also tells me the data type of the data set. So this is a 64-bit floating point number written in little endian for the traction change. And it has 26 impulses, or in this case, in some case, this will be the time steps, but in this case, it's the impulses. There's 31 places where I have that value with 2 components for each of those locations. It also tells me that, yes, this is a scalar for a vector field type. So we can add attributes into these Hdf5 files to have auxiliary information. If you want to see the whole file in sort of an ASCII form, we do H5 dump without any arguments, and it's going to dump out all the values as well as like the attributes. So my vector field type in this case was a vector. And so you see all of that for every single point within the data set. It tells you all the indices and it tells you all the values. So that's taken the binary data file and written it out as an ASCII in a specific format. So going back to our inversion script, In order to get the impulses in a particular order, we're going to do a sort on them. So there's a numpy command to do a sort. It tells us the indices, how to change the indices so that they're in order. So then we have sorted impulses, coordinates, and the values. We close our file, get our responses. In this case, again, our coordinates are in /geometry/vertices, and this output is for the displacement. So instead of vertex field slip, we have vertex field displacement. Impulses. And so getting the data, these are our fake observations. Again, it takes 3 lines to get, we have to open and get the displacements. And down here, we're just parsing command line arguments for what the impulses file is, what the responses file is, where's our data coming from, a penalty file, so a file with all of our penalty parameters, and then the output. The main body of after we get all of our penalty parameters, so our penalty parameters, they're in a text file, so we use just a load text. That's very similar to analogous to MATLAB commands to load in a text file with column data. And so now we're going to form our inversion. So we sort of combine our parameters, our observations. We form our matrix, so we got to do some reshaping, do transpose. We create our identity matrix for our minimum moment, which is multiplied by the penalty. Because we want a minimum moment solution. We're going to do some more manipulation of flattening things, concatenating them, putting in some zeros. We're forming, creating an array to hold our results. So we're going to do a inversion for all of the different penalty parameters that we have. And so we're going to do a sort of a suite of inversions where the solution is going to vary based on the penalty parameter. And so the number of inversions is equal to the different number of penalty parameters. So we get space for the inversion. Now to do the inversion, we're going to loop over the inversions. We set up our penalty. We're going to set up some output. And we're forming our generalized inverse matrix. So this is, you notice here we're going to tell NumPy to invert our matrix. And then we also have the transpose. Here's our solution, is basically dot our inversion matrix with our observations. We assign that to a specific point in our array for holding our results. And then we compute what the predicted solution would be based on our inversion, and then compute the residual minus predicted, and then print that out. And so you'll notice that this looks quite similar to what we'd have in a MATLAB. It looks a little different because we're using Python rather than the MATLAB scripting language. But one advantage you'll see is that we have the power of the Python language. So we can use all sorts of other packages rather than just those that will be in MATLAB. And then we'll save the results using the save text command, very similar to writing values from the MATLAB. So let's run the inversion. And so I'll go back to the terminal window here. And so in order to show how to run the inversion, there's the README in the greens function. We did step 2, generating the greens functions, and we have this big long command line to run the inversion. And so let's walk through that. We're going to call our Python script. We have our impulses file, which is from our computed using Greens functions. That's what our impulses are, so that's the fault output file. Our responses are the Greens functions dash points. That's our displacements at those points for each of those impulses. Our data, which are our fake observations, were generated in our EQSIM-points.h5 file. So normally we wouldn't have this in an Hdf5 file. We'd have it in sort of some geodetic GPS observation displacement vector file or INSAR data. So it would be in a different format, so we'd have to update our inversion script. Our penalty parameters is just a list of numbers that vary by one order of magnitude. We'll look at that very shortly. Penalty params.txt, and then write the output file to slipinverted.txt. So small inversion runs very quickly. So we had a penalty parameter of 1 times 10 to the minus 5. That gave us a residual norm of essentially 3 times 10 to the minus 6. Penalty parameter of 1 times 10 to the minus 4. That gives us a residual of about 1 order of magnitude greater. We go to a penalty parameter that's 1 order of magnitude larger. We get about a similar size residual. Now as we increase our penalty parameter by continuing orders of magnitude, we're getting quite large residuals. And then if the residual, notice that here these last two, very large penalty parameters and very large residuals. What does that penalty parameter file look like? It was just this list of residual values that we just went through. Now to visualize the results, I don't have matplotlib on this computer, but I have it on my Linux machine, so I'm going to try and log in remotely and display it on this machine. So I'm going to switch to X Windows, pull up a file here. Hopefully this will work. If not, the next time we can look at it when Charles is available. So it looks like my X Windows is running properly. So I actually have to run all of these simulations. But that won't take very long. Any questions while we're waiting here? So I think this is going to work. So I'm going to share my whole desktop here. And it's a little hard to see. Not sure how to increase the font size because I don't usually use the external. But since we're going to be displaying graphics, hopefully it won't matter. So I'm going to rerun my Greens functions problem on this machine. Rerun the inversion. So this is output dot functions dot alt dot h5 responses Greens functions points dot h5 data output EQSIM dot T is text out. Included text. And I don't know how to spell. So what did I get wrong? So it says I can't open some file. I must have specified one H5 file wrong. So my response is as an output. And I don't know how to spell Green's functions. There we go. There's the inversion. Thanks for the help. And so now I want to plot the results. I'm going to keep my fingers crossed here. Inverse. Oops. Inverse results. Solution is output. 5. Predicted output. Skip inverted. Did not like that. So it looks like I have an X Windows permission issue here. I think it's been so long since I've used X Windows remotely. Matt, do you remember how to do the set permission for remote display? A capital X. Keep my fingers crossed. There we go.
Brad,
Excellent.
when you SSH in, I usually just
here's our
forward
inversion
X,
results. So
so you
the
can do
solid
SSH
black line was
O,
our
forward X11 equals yes, and that usually works for me. Or I think it's actually
so that's our exact, our target solution. And as we've changed so these two far left ones are our biggest damping parameter, and so you can see why the residual was so large for those, because they really don't match our solution very well, but they definitely minimize the moment. Then as we add smaller penalty parameters, you can see we're starting to, it's trying to minimize the moment but match things. And so there's a suite of sort of solutions that do a pretty good job. They have sort of various amounts of oscillation due to our smoothing, that they're trying to fit this essentially uniform slip that tapers to 0 at 15 kilometers. So if I was to look at this and evaluate which one is doing, which one I have sort of the most confidence in terms of what penalty parameters to use, I would say, well, this sort of family of curves along here shows, just sort of moderate sensitivity or relatively little sensitivity to my penalty parameter. And so I would say, I'm relatively confident the slip distribution looks something like this, relatively uniform with depth, and then it's decreasing, and, this decrease is occurring somewhere between 12 to 17 kilometers. I don't really know parameters, they have significant deviation, so I think I've over-smoothed my solution in those cases. So that's it for this 2D Greens function example.